In this class, we are going to study topic 2, Newton's laws. We continue with the study of point dynamics, but we are going to focus on the description of Newton's laws. The three laws, which are called the first, second, and third laws, can also be stated as the principle of inertia for the first law, the fundamental principle of dynamics, and the principle of action and reaction. Let's finish with the analysis of some typical forces with which we are familiar. Both Jota and Amanda know that in order to be successful in the sports they practice, they have to take into account all the interactions that the environment makes on them. These interactions can be described according to this scheme that we analyzed in the previous class, and, for example, can be represented by these force vectors. We could think, together with Jota and Amanda, that we feel a great variety of interactions and therefore a great variety of forces. However, all the interactions that the environment imposes on us can be grouped into four large groups of forces. The first of these, the gravitational force, always appears due to the mass of the bodies. Here we have a typical image representative of the scope of application of this gravitational force, which is very well known to us, and yet it is the one with the least intensity. Another force that is quite well known to us and used is the electromagnetic force. In this example, what we have are photovoltaic solar panels, which, thanks to the electronic transitions of charges that are taking place in them, are capable of supplying electrical energy to this house. We also have the strong nuclear force, which is responsible for not producing the disintegration of the atomic nuclei in this case, and that the nuclei remain strongly united, which in principle can call our attention if we think that inside the nuclei what we have are protons and neutrons, and the protons have positive charge. Therefore, in principle, we could think about the great repulsion that there is going to be between these charges of equal sign, but thanks to the strong nuclear force, this spontaneous disintegration does not occur. In addition, we have the weak nuclear force, which is responsible for the emission of beta radiation by the sun, and therefore for the energy that with which we are very familiar and which we take advantage of, reaches us. We are going to study all these interactions, and Newton's three laws will allow us to analyze them very well. The first statement that we are going to analyze is the principle of inertia. This principle tells me that if there are no external forces applied on a body, or better, the resultant of all the applied forces gives me a null value, this body will remain in its state of rest in a uniform rectilinear motion. Let's see this experience in which Jota is playing with his skateboard. We consider that there are no external forces applied neither to him nor to his skateboard, and the motion is a uniform rectilinear motion. We have to keep in mind that the scope of application of this law and the other two that we are going to state are reference systems or spaces characterized by inertial reference systems, that is, reference systems that are in absolute rest or uniform rectilinear motion. It will be a constant throughout our class. Newton's second law or fundamental principle of dynamics tells us that the resultant force exerted on a particle is proportional to the acceleration that occurs in it, and that constant of proportionality is the inertial mass. Let's change now a little bit the analysis of the experience of Jota, who is again on his skateboard, but he meets in his way with this brick. There is an impact. The skateboard is no longer in its original state of motion. Jota tries to continue to maintain its movement, but the skateboard cannot because the normal with the brick appears. Let's see how it happens. Here it is. We see another experience where we could also analyze the forces that are applied. Jota could try to modify his state of motion by taking advantage of the interaction of the ground with his foot. With his right foot, he tries to produce an acceleration in his movement, taking advantage of the friction force that is going to appear. The mathematical formulation of Newton's second law can be expressed in this way: as the sum of external forces applied to the system we want to analyze equal to the mass of the system times the acceleration it will experience. In the International System of Units expressing mass in kilograms and acceleration in meters per second squared, the units we are going to use for the force vectors are going to be newtons. We are going to see how Jota gets a greater acceleration in his movement thanks to the action of his foot and the friction force that appears in the contact points between the foot and the ground. Here we see it clearly represented. we would have the vector force and how to get the value of the acceleration. We could do it from the analysis of the mathematical expression of Newton's second law. Finally, the expression of Newton's third law, or principle of action and reaction, tells me that whenever two bodies interact with each other, we have an interaction on the part of the first particle on the second particle that will be equal in modulus and direction, but of opposite sense to the one that the second particle will make on the first particle. In this representation, we have the impact of the ball when Jota is throwing it in one of his basketball practices with the glass that supports the basketball basket. The two vectors representing the interaction of the ball with the glass and the interaction of the glass with the ball immediately appear on the same line of action. The mathematical formulation of this third law of Newton would be this here, where the two force vectors are equal in modulus and direction, but opposite directions, and the direction is represented by this sign. When Jota had impacted on the brick through his skateboard, these two interactions were appearing directly, that of brick on skateboard and skateboard on brick, which led to modify the state of movement of the skateboard. Among the different types of interactions with which we are familiar and that we can describe in a more mathematical way through their vector representations, we have the weight force that appears due to the mass of the bodies. In this experience, Jota is throwing a tennis ball upwards, and we know that this tennis ball will spontaneously evolve to fall downwards. Because of what? Because of the Earth's gravitational field that will attract it. This interaction will therefore be conditioned by the mass of the Earth, which is of the order of 10 to the power of 24 kilograms, and the Earth's radius, which is an average radius of 10 to the power 6 meters. The acceleration of gravity that we can calculate thanks to this analysis that allows me to describe the law of universal gravitation is 9.8 meters per second squared. Now, the evolution of the ball is a downward movement, and that is because the vector representative of the weight force is a vector that has of module the mass by gravity, and of module I am going to take in a reference system, taking the vector j as unit vector representative of the y-axis and negative vector, since I am going downward in my evolution. Another force that we know that appears in many everyday experiences is the normal force, that is the force that appears whenever two bodies are put in contact through their surfaces. We will always have the normal force at the point or points of contact of the two surfaces, and it will always be perpendicular to these surfaces. Here we have it represented at the point of impact between the ball and the glass, but we have in mind that now what I am analyzing is the interactions on the ball. We have therefore the interaction of the glass on the ball through this normal, and we also know that the gravitational interaction will be acting through the vector of the weight force. Now, we see here, and we are going to analyze it now, in simple schemes, that this normal is not always going to be equal to the weight force. Let's analyze this diagram, where we have a body represented by this blue line, and the interactions that we have to consider immediately are going to be the terrestrial gravitational force by means of the weight vector and the normal. This normal in this case will coincide with the force weight mg of value mg, but in this other representation where the body is resting on a surface that forms an alpha angle with respect to the horizontal, it turns out that the normal will be referred according to this system of axes in this direction, while the weight in the vertical direction. In this case, the motion is not occurring in this direction, and in this case, the normal does not coincide with the weight. It will coincide with a value given by mg and the cosine of the angle. Another of the forces that we have, or interactions that we have to consider, are the tensions that are going to appear when we have ropes acting on the bodies. In this example, Jota is playing with a sphere through a rope to which this sphere is attached. We can imagine the circular trajectory that Jota is giving it, and we quickly know that if this sphere does not appear to the right, it is because there is a tension that appears at the point of attachment between the string and the sphere. The other interaction that I have to take into account, of course, is the weight force. Here I have another daily experience of two bodies that are hooked by a rope, and the natural evolution would be that due to the weight of this mass that hangs, then that system evolves to the right, with a velocity for body 2 represented by this vector that would be the same since they are hooked by a rope as that of body 1. The stresses will appear at the point of contact between the body and the rope, m sub 1 and the rope in this case, and t sub 2 for m sub 2 and the rope. Another force we have to analyze is the elastic force. This appears in systems such as springs or springs. In this case, we have Jota practicing a little bit an exercise to develop his pectorals, and we have this instrument formed by elastic bands. And we know that Jota, as he tries to produce a displacement of those elastic bands, each time separating me to his hands, the force that he has to do is much greater. Therefore, we could represent that elastic force associated with the rubber as being proportional according to this constant to the deformation it is producing. If I consider this scheme where the strings have the direction of an x-axis, that force with all its vectorial character, its modulus would be given by that constant that will characterize the type of rubber, in this case spring, and the deformation it produces by means of x. And the last force that we are going to analyze is the frictional force. This frictional force we know appears whenever there is a relative displacement between two surfaces in contact. It will have the direction of motion, but always opposing that motion, and the modulus is proportional to the normal in general. This constant of proportionality is defined by the coefficient of friction that will be static in the case that what we do would be to initiate the movement, and will be the coefficient of dynamic friction when we are already in motion. We see here Jota trying to produce a displacement of this big box. In principle, if we are not producing motion, what we have is an equality between the friction force and the force that is exerting Jota. At the moment we are about to produce the movement, we will be reaching the maximum value of that friction force, defined by the constant of proportionality of the coefficient of static friction and the normal. And when the movement has already occurred, we will see that the value of the friction force decreases slightly and will be given by the coefficient of dynamic or kinetic friction and the normal. We have therefore that if we analyze the value of this friction force is increasing as Jota is increasing its interaction until it reaches a maximum value given by the maximum friction force. At that moment, when the movement starts, the friction force will have a constant value, the dynamic friction coefficient times the normal. With this, we have analyzed the main typical, the most common types of forces we have. We have to have very clear the statements of Newton's laws, and that its scope of application is the inertial reference system. And we have taken a first contact on how to represent the most common forces with which we are familiar. In the next class, we are going to analyze another very important physical quantity in the scope of the study of point dynamics, the quantity of motion. Until then.